The final section of this chapter, I will introduce to you the Michelson interferometer. The Michelson interferometer is formed by one half-transmitted mirror and two reflected mirrors. As incident light hit the half-transmitted mirror, this is the scattering matrix of the half-transmitted mirror. We will induce the two-light beam goes from the lens A, lens LA, and the lens LB. And for the lens LA, this is the transmitted light. It will go this way and hit the reflected mirror and go back to the half transmission mirror. And then for this path, the reflected light beam will have the corresponding amplitude of this turn, and he will go this way, hit the reflected mirror, and reflected to the original half transmitted mirror. As these two light beams go back and arrive the half transmitted mirror, both of they will be separated into another two light beam in these two directions. Then we will have output B1 here and output B2 here. And I have to remind you that as light beam go along this path, it will accumulate the phase delay by the 2LA length difference. And if the light beam go along this path, the phase delay will be induced due to the length of 2LB. Okay, so this is LB, and go to there and go back will have 2LB length difference. According to what we have said, we can write down the expression for the output power or output amplitude at port 2, because we have set the observation plane at the port 2 here. And our purpose is that to find out the total scattering matrix of the whole system. Okay, so for the Michelson interferometer, we can plot it in a simpler way like this. The total scattering matrix can be written as S scattering matrix is S11, S12, S21, and S22. At port 1, we have input A1 and output B1. At port 2, we have input A2 and output B2. And of course, we have no input at port 2, so A2 is 0. Okay? And according to this figure, we can say that the amplitude of B2 can be written as, consider the amplitude of B2, it combines two sources. One goes from the length LA and the other goes from the length LB. Okay, so first consider this path. For this path, we have A1, we start with A1 and transmit the half transmission mirror. We will have the corresponding parameter J over square root of 2. And as the light beam go from here to here, it will accumulate phase difference by exponential minus JKLA. Okay, as the light beam hit the reflected mirror, the amplitude will be multiplied by minus 1. And then it will go back to this half transmitted mirror, and again it will accumulate the phase difference, and then will hit the half transmitted, will be reflected by the half transmitted mirror, so we must multiply it by the factor minus 1 over square root of 2. So this is the component go along this path. Another component go along this path. we still start with A1, and first, reflected by this mirror, we must multiply it by minus 1 over square root of 2. And go along the length LB, it will have the phase delay by this turn. And hit the reflected mirror with the parameter minus 1. And go back to the help transmitted mirror, another phase delay will be induced. Sorry, this should be B. And then this component will pass the help transmitting mirror with the parameter J over square root of 2. So the output B2 is composed of these two components. Okay, so after some arrangement, you can see that these two components can be written as J over 2 times exponential minus J 2k LA dot A1 times A1, sorry, plus J over 2 exponential minus J 2k LB times A1. And we know that according to the scattering matrix, is if A2 is 0, then B2 can be written as S21 times A1 as A2 is 0. So from this expression, you can easily find out the expression for S21, right? So we rearrange this term. And this expression can also be written as the following form. If you take common term here, the above two terms can be written in this way. Okay, then the reason we write it in this way because it can be transformed to cosine function. So we write the final result will be JA1 times exponential minus JK LA plus LB times cosine K LB minus LA. Okay, so clearly you can see that this will be S21 A1. So this part will be S21 J, and this part will be S21. And following the same way, you can easily write down the expression for B1, the output at port 1. It can be expressed as JA1 times exponential minus JK LA plus LB times sine function K LB minus LA. Okay, and we also know that B1 can be written as S11 A1 as A2 is 0. So clearly, this part will be S11. And from these two equations, you have obtained S11 and S21. As we know, due to the symmetry of the scattering matrix, S21 will be the same as S12. So you have obtained these three components. As for S22, you can obtain S22 following the same process by interchange 1 with 2. Okay? So we can easily obtain the scattering matrix of the Michelson photometer, which is written in this way. And according to the expression of the scattering matrix, you can obtain the transmitted power at the port 2. Which is the square of B absolute value of B2, and this term can be obtained by the square of the absolute value of S21 times A1 square. Okay, then the transmission capital D is defined as the square of B21 over the square of A1. And you can take the expression of S21 into here, the square of B2. And this will be S21 square. And take the expression of S21 into here, the result will become cosine square K times LA minus LB. So you can see that the transmission of the Michelson interferometer will be a cosine function, cosine square function, right? So if you can easily find this expression to find out the transmission minima. The transmission minima will occur at K times LA minus LB. This value is half pi times 2m plus 1, for m is an integer. Then this means that if the length difference LA minus LB is quarter wavelength times 2m plus 1, then you will have transmission minima. If you want to have transmission maxima, you must let K times LA minus LB to be pi times m. As a result, LA minus LB should be m times half lambda. So if the difference between two arms satisfy this condition, then you will have the transmission maxima. Let us plot the transmission of the Michelson interferometer. This axis is the transmission, and along this axis we define it as LA minus LB. So you can see that as LA minus LB is 0, you will have transmission maxima. So let me plot the transmission. It will look like in this way. As LA minus LB is 0 or half lambda or minus half lambda, you will have transmission maxima. And if LA minus LB is quarter wavelength or minus quarter wavelength, you will receive transmission minima like this. Okay? And please compare the transmission with the Fabry-Pérot. As we know, the transmission of the Fabry-Pérot as reflection R is large, it will look like in this way. But for Michelson interferometer, it will be the cosine square function like this. So the output performance of these two interferometer is quite different. Okay. Besides, the Michelson interferometer is frequently used in detect material index or material thickness. For example, if we have already known the length difference between LA and LB, then you can place an unknown material here with index n and the thickness d. And if you know the index n, okay, then the thickness d will have a corresponding phase contribution along this path, and this contribution will also change the output power at the port 2, right? So you can find out the thickness of the material by the variation in the output power. Okay. Similarly, if you know the thickness here, and you can use the power variation to obtain the phase delay variation here, and according to the phase delay variation, you can find out the material index N for you. So this kind of microsensor interferometer is frequently used to sensing or to find out the material thickness or material index for the researchers.